Okay, let's get going. Hello, everybody. My name is Jem, and welcome to Markov Processes. I assume you can hear me. Can I get a thumbs up? Awesome. I love this course, and I'm going to say that it is my favorite thing to do. And then some of you are going to call me out and say, no, you said that about mathematical statistics. That's actually my favorite thing to teach. But Markov is what I do. It's like my research. I'm a Monte Carlo person. So I'm so glad to see so many people signed up for this. I think we're going to have a lot of fun. Um, and so before we get going, I guess I have to do some, syllabus stuff. So I am going to share the Canvas page with you. And I don't want to spend too much time on this because you can read, I assume. um, so when you log into the Canvas page, you're going to see something like this. This is actually a line of people forming a queue, and that's there because queuing is a big part of this course. So I think the formal title is Markov Processes, Queuing Theory, and Simulation, or something like that. I've just abbreviated it to Markov Processes. But queuing is the science of waiting in line. And by the end of this course, I want to convince you that if you go into a grocery store and you get your stuff and well, most people are doing self-checkout these days, but if you look at the different lines to get out of the store and you make a decision, you should stay there. You shouldn't move over when the next line starts moving, because we can prove using Markov processes that on average over your lifetime, if you're the kind of person that keeps switching and updating based on what you're seeing, you'll actually spend more time in line. Yeah, so if you get anything from this course, it will be how to check out in a grocery store. Um, so there on the front of this page, there's a Start Here button, and this is really kind of unimportant because it leads you to this syllabus and also to CU resources, which is all the like legalese information that the university makes us put in here. So I am going to go to the syllabus. Okay. So yeah, there's the queue, people waiting in line. Here's the Start Here button, which is unimportant. It'll take you everywhere that you will go to using other buttons. See your resources, just legal stuff. This is a button, Evolving Course Notes. And if you've taken a course with me in the past, um, I usually have a pretty decent set of notes put together that become the textbook. I don't have that for this course, and I just made the decision yesterday, which is why the Canvas page was so delayed, because I typed up 62 pages yesterday. So this is just a start, and most of it is review that you can look at if you need to, but you don't have to. And I am going to get ahead of you and stay ahead of you. But right now I only have chapter 1 here. So I'm going to be working on chapter 2 today and tomorrow, and I'll stay ahead of you. Today we're going to cover section 1.9 on conditional probabilities because that's what Markov processes are all about. And my advice to you is to check out 1.9. And then if you need more review, the next most important section is 1.6, which is important distributions for the study of Markov processes. So believe it or not, there's no normal distributions in this class, but there are definitely exponential distributions and gamma distributions and Poisson distributions. And so I've just, kind of picked out some of the important ones here. So let me go back out to the main page. There is a button that says office hours. There's not much there yet. So we are fortunate to have 3 TAs for this course. And so there's going to be a lot of opportunity for you to get help from myself as well. And this is going to be a big clickable calendar of office hours, which will be up in maybe today, possibly tomorrow, as everyone finalizes their schedule. So let me go back and let me click on syllabus. Okay, this is my office, ECOT 337. Phone number, email, phone's not great. I don't remember my PIN. Email, great. I'm always in front of my email. I am going to continue to hold office hours over Zoom throughout the entire semester because I live in a very immunocompromised household. and I don't really want to crowd in my little office. So I'm not sure what the other TAs are going to elect to do. Oh, look, Sage came in here. So Sage is the lead TA here, and he has announced his office hours. And I'm gonna summarize all of this for you in a nice clickable table tonight. So there is no textbook. I do have some suggestions for you if you need a textbook. And so there'll be evolving course notes. And this is what I was saying to you before, that I am working to get ahead of you, and I will stay ahead of you. So without the course notes being ready, you don't have a table of contents. So I made a topic list to give you an idea of what this course is about. I realize a lot of these things probably won't make any sense to you until you actually learn them, and I need to still tell you what a Markov process is. But one part of this course is simulation, and I just wanted to let you know that it is a relatively small part of the course. I've had a few people come here looking for a Monte Carlo course. MCMC stands for Markov Chain Monte Carlo, and it's all about simulation. And this course is about Markov processes. There's a lot of theory first, and then we can use that in simulation. But simulation is a relatively small piece, so I don't want you to be disappointed if you came here for a simulation course. Homework. Homework's going to come out every Wednesday and be due the next Wednesday by like right before midnight. We're going to use Gradescope. If you haven't used that yet, there'll be instructions coming out. 2 lowest scores dropped. I can't accept late homework in a class of this size. It just gets crazy out of hand, like a floodgate. Whenever I do, I spend 2 weeks after I finish grading the finals, grading homework, because I don't feel it's fair to give them to the TAs, so I keep them, and then they just pile up, and it's a mess. So 2 homework scores will be dropped, and if you really have, like, if you're getting sick, let's talk. We'll work something out. But that's the basic homework policy. So simulation, as I was saying, is a relatively small part of this course, but you're welcome to use any language you want, like Python or MATLAB or Julia. I know there's a few people who have never done any sort of programming, and so for those people, I'm going to use R as an introductory language. Now, I know those of you who have done programming are probably groaning in your head right now. R is not the best language for simulation because simulation is big, like cranky, crunchy, loopy stuff, and R is not that great for that. But it's really easy to get up and started if you have no experience, and it will be fine for the level, the amount of simulation we're going to do, really idealized problems here. So if you can use your favorite language, but I will put out some basic R tutorials, and if you know nothing, you can use those. And if you know another language and want to learn R, you can use those as well. Okay, so quizzes. This is something totally new for me. I know a lot of you have been in my courses before. I usually just say, as long as you get your stuff in on time, I don't care what you do. I would hope to see you. I'd hope to have good attendance, but I'm not going to score you on that sort of thing. But over the last 2 years, I have really seen a decline in people's understanding and performance through the pandemic, and it's totally understandable. The point of these little quizzes, which are only going to be 5% of the grade, there's going to be 1 or 2 a week, and the point is they're just auto-graded. They're like multiple choice things. It's just to keep you a little bit engaged. It's not really going to be a big part of your grade or a big deal, and you can retake them as many times as you want over like a 2-week period, which I know kind of defeats the purpose of keeping you engaged. I wanted them to just be like every 2 days, but yeah, thanks, Chan. I also didn't want to put too much stress on you. So these are just, ways to get feedback quickly, just to keep you engaged. Sometimes it might be just as little as a definition. They're not a big deal. It's just like, hey, check in with Markov. And why do I think we might have that problem again this semester? So we're supposed to go live in 2 weeks. Number one, I don't know what's going to happen, if the university is going to shut down again, or, we could end up remote. but mostly there is a remote section of this course, a truly remote section. People that are going to be joining us over Zoom in the physical classroom. And because of that, there will be videos posted and you can all look at them at any time. But that makes, I don't know, that makes it really easy to lose the class, right? You know, I'm busy, I'll just catch up on these videos later. So that was kind of the point of the quizzes as well. The classroom is in the basement of the engineering center and it's a studio classroom. I'm not recording this time. There's a group of people in a room next to us recording and listening to us. It's going to be super creepy. There are like long tables, you know, like for desks, and every spot has a microphone built into the table. So I just want to give you a heads up about that. You know, if you're like whispering during class or throwing your books on them, yeah, it is super creepy. So here are some suggested phrases for you. Wow, this is the best class ever. Um, Gem is awesome. No, I don't know. But they will, they're not going out to the public. Only you guys will get Zoom links, but I don't know exactly how that's going to work from the classroom. We're going to learn that together. And in the classroom, your faces and names will never appear for privacy. And right now, as I'm recording, I do remove your faces and names before I post it. Okay, 2 exams. They are in the evenings on Thursdays. Why? I want to give you more time to take the exams. Now, this was not in your schedule when you signed up for this course, so check your schedule, block it out if you can, and let me know early on if you can't make these exam dates and times, and we'll work something out. But the idea is to give you more time to work on the exams. So they're designed to be in-class 50-minute exams. Previous students may disagree, but that's usually my intention. And so you're just getting a full 2 hours. I mean, seriously, historically, some people have left at 25 minutes. Most people leave around an hour, and some people hold on to the very end. And then to try to give you some of this extra time back that you're putting in, we're not going to have class the next day after each of those exams. So cool, right? And then there'll be special instructions for the remote students, and I'll be contacting the pure remote students as well to talk to you guys about this. So here's the breakdown in scores. Just 5% for the quizzes. Your 4 lowest will be dropped. If the quizzes are really hurting you, it really, again, the point was to have you check in. So it's more, I'm not going to let them hurt you. It's more like if I see you're not doing them, then I'll check in and say, you know, are you okay? Are you behind? Do you need help? Homework, 25%, 2 lowest dropped, 2 midterms at 25% each, and the final exam at 20%. I like to keep that a little lower because that's a really stressful time of the semester. So if you're taking the course for graduate credit, this course is listed 5 different ways. So by the way, if you're on the wait list, this should all be shaken out by Wednesday because there are 5 different sections with capacity. Some are full and some are not, and it's really determined by room capacity. And so I'm going to have the capacities switch so everyone can be in the section they want. So if you're on a wait list, you won't be for long. Graduate students, they will have an additional problem or 2 on each homework assignment. They're going to get some take-home problems in addition to the in-class midterm, and their midterm scores are going to be 70% in-class and 30% take-home. You'll be given a lot of time to work on those take-home problems. And you could potentially be held to different standards in grading. So we try really hard to keep the rubrics clean and make sure everything is nice and fair. But if you're ever like, hey, why did I get 5 points off for this? And this guy only got 2, you should look into it. It might be a problem, but it's likely that one of you is a grad student and one of you isn't. So there may be differences there. Okay, I'm going on way too long. That's the last thing I want to say. Here are 2 references if you would like, you know, textbooks. I just realized right before class, my second link is dead, so I'm going to fix that. The first is called Essentials of Stochastic Processes by Richard Durrett. And this is a really good book. And some of the other instructors in applied math use this as the textbook for the course when they teach it. I just have never liked it for that. I think it's an awesome, awesome reference, but a little bit dense and hard to learn from. But there is a PDF linked here. I'm not going to click on it because I don't want the loading time. So there's a free copy. And this other book, An Introduction to Stochastic Modeling by Taylor and Carlin, this one is very friendly and readable. This one is a little bit under the level of the course, and the first one is a little bit over the level of the course. So Taylor and Carlin have many additions. They all have the same basic information though, so any addition. But watch out, there is a book by Carlin and Taylor called Stochastic Processes, which is a whole different kind of like measure theory league. So I don't want you to see that and get scared off. You're looking at the wrong thing. Okay, I think that's all we need to talk about. There may be other things, but I'll let you take a look. And oh, look, Sage has been in here. I think he's actually in this meeting, but he set up a Slack for the course, which is awesome. A great place to get help and to discuss things with each other. So thank you, Sage, for setting that up. I'm going to start sharing my screen. And if anyone has any questions, let me know. You can speak up at any time or type your question in the chat. And if you are shy and feel like you have a stupid question, you really don't, but no one believes me. So type a direct message in the chat and I'll answer your question without revealing who you are. So I'm going to go for my screen share here. Let's do this. So I need to define a Markov process for you, and I'm still working on it, and we are going to get there, but I can't do it until we talk about conditional probability. And probability is a prereq for this course, but everyone's in a different boat, and they've had it years ago or not so long ago, or they skipped it, or they said this class would probably do instead. So I want to do just a little bit of review, and it is about conditional probability because Markov processes they're all about conditional probability. And so that's where you have, given information. So actually, before I say that, I want to talk really briefly about random variables. Sorry, my handwriting will get better. So random variables in probability and statistics, they're always denoted by capital letters. That's the convention. And so we're going to use things like X, Y, and Z. You can use any letters, but those are the most common ones. And you might not be able to tell what's capital and what's lowercase, but my lowercase letters are a lot curlier. And I think within the context of the problem, it's going to be pretty clear. But, ask me at any time if something is a random variable or not. And so random variables are functions. They're mappings. So they're mappings or functions from the set of all possible outcomes of an experiment that involves randomness or probability to the real numbers. Gosh, do you think I haven't written for 3 weeks? My handwriting is not great, but it's much better than this, so this will smooth out. So what do I mean by this? As an example, let's flip a coin. And it could be a fair coin or not a fair coin, but let's flip a two-sided coin with heads or tails. And then I'm going to define a random variable capital X. I'm going to define it to be 1 if we get heads on the coin and 0 if we get tails on the coin. So you can see this is a function that took in the output of the experiment, heads or tails, and spit out a number. That's all a random variable is, but sometimes it's illuminating to think of them like this as a function of outcomes of an experiment. And this random variable is discrete in that it only takes on some discrete values. That doesn't mean a finite number of values. A discrete random variable could take on all, potentially all integers, or they don't even have to be integers. So you can have a random variable that takes on the values maybe 0, 1/10, 2/10, 3/10, up to 1, and that's still discrete as long as they can be separated on a number line. And a discrete random variable has something known as a probability mass function associated with it, or a PMF. And these are always denoted by just like an f of x, and they are the probability that x equals x. So if we have a fair coin, which I really haven't specified, so I'm going to write that here, a fair coin, then we are going to get 1 with probability 1/2 and 0 with probability 1/2, and we're going to get 2.8 with probability 0. So we want the probabilities in here. This is going to be 1/2 if x equals 0 or 1 and 0 otherwise. And so you're plugging in one of the x's and you're spitting out a probability. That's a probability mass function. And this particular random variable, the 0, 1 situation, comes up so often that it gets a name. This 0, 1 situation is known as a Bernoulli random variable. And it could be a little more, it could be much more general than 1/2, 1/2. So let's say we have a potentially unfair coin with little p is a parameter that's going to be the probability that we get heads on the coin. So in the previous example, this was 1/2, but maybe it's a little more general. If we take a random variable x that is equal to 1 with probability p and 0 with probability 1 minus p, and this will have probability mass function. The probability that x equals x is going to be p, 1 minus p, or 0. It's going to be p if that little x is 1, 1 minus p if the little x is 0, and 0 otherwise. I know some of you are bored out of your minds right now. I just want us all to be on the same page for when we really get into Markov stuff on Wednesday. Then this kind of random variable and this probability mass function, this comes up so often that it gets a name. So if you are, I don't know if you could see me in a little box, but if you imagine like an x-axis and having a 0 and a 1, and sort of making a histogram which shows you the levels p and 1 minus p, as you change p, it changes how those values are like distributed. And so we also call this a Bernoulli distribution. So we say that x has a Bernoulli, that's just a guy, Mr. Bernoulli, distribution. And it's not completely described until you give that parameter p. So with parameter p for some p between 0 and 1, you know, technically inclusive. We might have a two-headed coin or something like that. And we write, when we talk about naming any distribution, we write the random variable and then a squiggly line, and that can be read has the distribution. And I'm going to write Bernoulli, and then open and close parentheses, I'm going to put the parameter p in there. So a discrete random variable. Let me know if you're not okay, or if you want me to go back and scroll up if you missed something. Right here was where I was going to say, okay, let's quickly talk about continuous random variables. But I don't want to waste our beginning of the semester energy on that. So I want to define a Markov process, and eventually we'll talk about continuous things. So a Markov chain or Markov process is a stochastic process. And so first I want to define this, a stochastic process. The word stochastic essentially means random. And the word process is something that is evolving over time. So a stochastic process is a sequence of random variables. All right, and I'm already in with the abbreviations. That's a sequence of random variables. And the time that the indexing of the random variables could be discrete or continuous, and the random variables themselves could be discrete random variables or continuous random variables. So yeah, let me be a little more formal here and say a stochastic process is a time-indexed collection of random variables. And a Markov process coming soon, there's an additional property, is a time-indexed collection. Sorry about the mess and the time, but I do think it's so much better to not just bring up slides, to be a little more organic with the math. I don't know, you might disagree. We could talk privately, you can complain and maybe I'll change it. Okay, so in discrete time, we may start counting from time 1 or we may start counting from time 0. We do both in Markov processes. So we have a sequence of random variables, maybe x0, x1, x2, on up. And we can talk about the whole collection by using brackets like this. So curly bracket xn, and then writing like n equals 0 to infinity. This is the entire sequence or collection. And it is different from just xn. This is one of the random variables, the one at time n. And the collection notation is also written, a little more briefly as just like xn. But when it has brackets around it, it is referring to an entire collection or process. And these random variables could be discrete or they could be continuous. And then we have continuous time. So in continuous time, I don't know, it's okay, I guess, to use an n, but it's really weird, right? Like letters like n and m are integers usually in math, and letters like s and t are usually used to denote continuous time. So I can't list them out in continuous time, but I can talk about the collection of random variables, maybe x sub t, and then say for all t greater than or equal to 0, something like that. Or, if we're rushing, just xt, because we're going to be writing this a lot. Or, and this is a convention that I want to use throughout this course, I'm actually you don't have to do it either. You'll get full credit on your homework, even if you write it in a slightly different notation. But I am going to use parentheses whenever I'm talking about continuous time. So it's going to be more like x of t or x of t. So I am going to use, and I'll remind you over and over again, so you'll eventually, you don't have to remember this right now, but I'm going to use subscripts for discrete time and like parentheses for continuous time. And these sequences of random variables indexed in continuous time, they can take on, they can be discrete random variables or continuous random variables. So we sort of have 4 different things to consider here: discrete time and a discrete space that the random variables live on, discrete time and a continuous space, continuous discrete, continuous continuous, and awesome, thanks. The majority of this course, the first half of this course, everything is going to be discrete time and discrete state space, which is why I decided to put off reviewing the continuous PDF stuff, because we have more time that we can do that and not, again, waste our beginning of the semester energy. So yeah, okay. That's a stochastic process. Now, a Markov process is a stochastic process with a property known as the Markov property. And I'm not ready to define that because it's defined in terms of conditional probability. So here's where we're going to do a conditional probability review. And if you've come out of mathematical statistics, which is not a prereq for this course at all, then you've done some quite sophisticated probability, but you probably haven't used a lot of conditional probability. So when I start different courses like mathematical statistics and Markov processes and time series and simulation, pure simulation courses, I usually start off with a probability primer, but they're all very different. And this is conditional probability. So let's talk about conditional probability. And it won't be completely boring if you know this stuff, because I'm going to go kind of maybe deeper into it than you have. So a review of conditional probability. And then we can define what a Markov process is. Probably most of you know at least basic conditional probability. So I've got my deck of cards, right? And I randomly select a card and I ask you, what is the probability? So you don't get to see it, but what is the probability that this card is a king? And a standard deck of American playing cards, there are 4 kings and there's a total of 52 cards. And if they're truly randomly shuffled, then all cards are equally likely to be drawn. So the probability of getting a king is 4 out of 52, right? So I'm gonna select one card randomly from a well-shuffled deck of 52 cards. And we can talk about the probability that it is a king. Hopefully this notation makes sense, a P for probability, and then I'm just writing the word king. And that is 4 out of 52, or 1 out of 13. You don't have to simplify any answers in this course. But, well, maybe if you're doing like a multi-part problem and your answer might go on to feed the next part of the problem. But 4 out of 52 is a fine answer. Decimals are okay too, but if you have rounding error, like why bother when you can write the actual fraction? I don't know. It's personal preference. Okay, so conditional probability. That's when I look at this card and I give you some information. So I say, this is a face card, and that means it has a face on it. And in 52 cards, there are 12 face cards. There are 4 kings with kingly faces, 4 queens, and 4 jacks. So if I tell you it's a face card and now ask you the probability it's a king, things have changed. The world has shrunk a little bit. And out of 12 face cards, there are 4 kings. So that is the idea of conditional probability. So let me write that down. If I tell you the card has a face on it, it is a face card. And there are 12 in a deck. Again, 4 jacks, 4 queens, and 4 kings. What is the probability it's a king? This is conditional probability. You have been given information, and we're going to write this like this. So the probability it is a king, and then a horizontal line, which can be read given it is a face card. So we have a formal way to do this, but you know how to do this. There are 12 face cards and 4 kings, so I have a 4 out of 12 chance, or 1/3 probability or chance of it being a king. And what we've done is we have shrunk the universe of possibilities, and Venn diagrams take you a long way in rules of probability. So you know those rectangles with circles in them? If you think of probability as area, you can get a lot of rules of probability out of Venn diagrams. So you're probably used to seeing events, like in probability, they're usually denoted by a capital A, B, and C. A could be the event that the card is a king, and B could be the event that the card is a face card. If you look at a Venn diagram, which is, you know, a rectangle with some circles in it, and you think of probability as area, let me write that, I was going to write equals, but think of probability as area, and think of the total area of the rectangle as 1, then you can get a whole lot of rules of probability. And don't worry, I'm not going to drag you through them, but I'm just going to write one down just to give you the idea. So if you want the probability that an event A happens union with B, A union B, this is A union B. So you want that total area, and it can be made up of the area in A plus the area in B. But in doing that, you've double counted the intersection. So you need to take that out. And I'm sure this is not news to you, this rule, but I'm just trying to say that I don't have the brain space for rules. So draw pictures and you'll get there. And the same thing goes for conditional probability. So let's talk about conditional probability. The probability that A happens given that B happened. Again, that horizontal line is read as given. So I'm going to draw a couple of sets. And unless I'm specifically given that they're disjoint and separate, or maybe one is contained in the other, I would always just draw them like this, just kind of give them a chance to overlap a little bit and make this a little better. So this is saying, given that the event B happened, B is like, I saw a face card, what is the probability that A happens? So all you're doing there is you're shrinking your universe. This is not the greatest graphic. I am removing everything but B. Like the universe has shrunk to only include this set B. And then I have to say, given that B happened, what's the probability I'm in A? And that's going to be the relative area of this piece to B. And so that is the definition of conditional probability. The probability that A happens given B happens is the probability that A intersect B happens as a proportion of the total area or probability for B. Yes, come back. This will speed up. I just don't want to take off on the first day because then some people are lost. I know some of you are really bored, but it's gonna get good and pretty fast. So if we go back to our king and face card scenario, what's the probability it's a king given it is a face card? This is the probability, let me go to the next line. This is the probability it is a king and intersect and a face card over the probability it is a face card. And this is probably not how you computed it when I asked you this probability before, but we'll get the same answer. So to be a king and a face card means that, just being a king already means you're a face card. So we don't need that. It's like, this is the set of face cards and these are the kings. So the intersection is just going to be the smaller set over the probability of a face card. And the probability of getting a king when you draw randomly from a deck of 52 cards is 4 out of 52. The probability of getting a face card is 12 out of 52, which is 4/12 or 1/3. So the same thing we got before, but this time by a formal definition. Okay, I have more review, but this is incredibly boring. We have enough right now. No, I have one more thing to tell you, and then we can define Markov chains. So the next thing I want to do is talk about random variables in terms of conditional probabilities. Let's go back to random variables. So suppose that X and Y are discrete random variables. Okay, so if X and Y are discrete, then we can talk about the probability that X equals 3 or something like that. For continuous random variables, there's just way too many possibilities, and the probability that a continuous random variable X is equal to a particular value is always going to be 0. But yeah, we can talk about the probability that X equals 1, or more generally, the probability that X equals some X. We already saw a formula like this for the Bernoulli distribution. And joint probabilities are indicated with a comma. So if you see the probability that X equals X, comma, Y equals Y, this is really saying and it's really just an intersection. And it's really the same thing. You wouldn't do this, but I'm just going to do this one time. It's really the probability of A intersect B where A is the event that the random variable X came up to be that little x. The event that the random variable x is observed to be little x, and B is the event that the random variable y is equal to little y. So in that sense, you can use all the rules of probability that you know with sets, and we are ready to define conditional probabilities for random variables, at least in the discrete case. So the definition of the conditional probability that x equals x, given that y equals y. So I won't keep doing this, but I want to do this as we start. So this is the event that x equals x, given that you will have already observed that y equals y. It's just the intersection over the second one. This is like the event A, and this is the event B, and intersections for random variables, ands are denoted by commas. So this is the probability x equals x, comma, and y equals y over the probability y equals y. So all your set theory is going to work for random variables, again, by defining events this way. Oh, please come back. You're going to learn not only how to shop in a grocery store, but how to catch flies. I have a lot of examples with insects in them. We are ready to define a Markov chain or Markov process. So it is a stochastic process. And the word chain, it means the same thing. It is typically reserved for a discrete time process, like chain, like links, discrete links of a chain, but no one's going to care if you use that the wrong way. So here is a definition. You know what? There's one thing I forgot, and please excuse the scroll. When defining a stochastic process as a sequence of random variables, it is conventional to have each and every random variable live on the same space. So if you're talking about a random variable x0 that could potentially take values 1, 2, and 3, and then x1 can potentially take values 4, 5, and 6 only, then when you talk about them together, you're talking about the space 1, 2, 3, 4, 5, 6, and then this will have probability 0 for parts of that space. So it is convention that they all live on one space that we call the state space. So I need to write that here. And we're going to call this S. Some people call it omega, but for stochastic processes, it's usually a capital S. Now we can define a Markov process. Yep, here we are. We're ready to go. So here is the definition of a Markov process or chain. Ultimately, they're going to have discrete time, discrete states, and continuous states. Right now, we're going to do discrete and discrete. So I'm going to let S be a discrete set or state space. So these are going to be, the possible values that these can take on. Like S in the Bernoulli example, we could take on the values 0 and 1. And then let's define a discrete time stochastic process, xn with parentheses, not parentheses, sorry, brackets. Without the bracket, I'd be talking about the nth variable in the sequence, but this is the whole sequence, is a Markov process or chain. And chain is definitely, I don't know why this one got the parentheses, it's definitely the more common language here. So chain is for a discrete time process. So it's got to be a stochastic process, a sequence of random variables, and the probability that the sequence at time n plus 1 is equal to some value j, given at time n, it was some value I, and at time n minus 1, it was some value. Now I can't keep using letters here because n is variable. So I'm going to say I n minus 1 down to x0 equals I0. This big conditional probability is the probability that xn plus 1 equals j given xn equals I. This is known as the Markov property, and it is what defines a Markov process or Markov chain. So there's going to be a lot of calculations where I'm doing something and then I suddenly have an equal sign and put like an MP over it. And that means I'm using the Markov property at that point. And I'll say that many times. We're almost out of time here, but what does this mean? I'm going to draw a picture. What you have is some state space, and you have time, right? And you've got maybe time 0, 1, 2, 3, and then we're going to have some, I don't know, just because it's discrete doesn't mean it has to be integers, doesn't mean they have to be non-negative. I'm going to draw it that way. So we're going to have, potentially the value 2 at time 0. There's going to be a whole distribution that says, oh, we're going to be at 2 with probability 1/3, and we're going to be at 4 with probability 1/8. There's going to be a probability distribution associated with the chain at time 0. And then it's going to evolve in some way involving randomness. And the entire point of the Markov property is that once you know where you are, where you go next, yeah, it's not determined. It is a random variable, but it depends only on where you are and not where you were. So if I had time, I would write that in quotes right here. Where you go depends only on where you are and not where you were. That's what a Markov chain is. But yeah, where you go depends on where you are. Now, that doesn't mean, last thing, that all the random variables, like this is x0, x1, x2, it doesn't mean they're independent, right? Because x5 depends on x4, which depends on x3, which depends on x2. But there is this kind of like, you can drop the history when you know where you are. That is how you define a Markov process in discrete time. I am out of time. I hope you come back. As you can tell, it's getting good right now. So yeah, thanks for coming. And I will see you next time on Markov processes.